Imagine a signal so powerful it crosses billions of light years in the blink of an eye. A burst of energy so intense it outshines entire galaxies. Yet it lasts no longer than the snap of your fingers. This isn't science fiction. This is the reality of fast radio bursts, or FRB, one of the most baffling phenomena in the cosmos. These millisecond-long radio waves, erupting from the depths of space, carry more energy than our sun emits in decades, and their origins remain one of astronomy's greatest unsolved puzzles. Just last year, astronomers detected an FRB so bizarre it defied every explanation, a signal repeating in a pattern so precise. It sparked wild theories from alien civilizations to collapsing neutron stars. But here's the thing, we still don't know what's really causing them. That's the magic of FRBs. They're like cosmic Morse code, whispering secrets from the farthest corners of the universe, daring us to decode their message. Some come from galaxies so distant, their light has traveled for half the age of the universe itself. Others repeat unpredictably, like a radio station tuning in and out of existence. And then there are the ones that just vanish, leaving behind nothing but questions. What could possibly generate such titanic bursts, colliding black holes? Exploding stars, or something even stranger, something we haven't even imagined yet? Every time we think we're close to an answer, FRBs throw us another curveball, reminding us just how little we truly understand about the cosmos. That's why today we're diving deep into the 30 biggest mysteries surrounding these enigmatic signals. From the eerie patterns of repeating FRBs to the mind-bending theories about their sources, we'll explore the cutting-edge science and the tantalizing possibilities that keep astronomers awake at night. This isn't just a story about distant radio waves. It's a journey into the unknown, a chance to stand at the edge of discovery and peer into the darkness. So buckle up. By the end of this, you'll see the universe in a whole new light. And you might just find yourself staring at the night sky, wondering what else is out there waiting to be found. The story of fast radio bursts begins not with a live observation, but with a cosmic cold case buried in old telescope data. Back in 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through recordings from the Parkes radio telescope in Australia, data that had been sitting untouched for 6 years. What they uncovered would rewrite the textbooks. Hidden in those static-filled recordings was a single, blistering burst of radio waves lasting just 5 milliseconds, yet packing the energy of 500 million suns. It came to be known as the Lorimer Burst, and it shattered everything astronomers thought they knew about radio signals from space. Here's what made it so shocking. First, its origin. By analyzing how the burst's lower frequencies arrived slightly later than the higher ones, an effect called dispersion, they calculated it had traveled an unfathomable 3 billion light years. That meant whatever produced it hadn't just happened in our cosmic backyard. It had erupted when Earth was barely 1 billion years old. Second, its sheer power. In those 5 milliseconds, it released more energy than our sun does in 30 years. And third, the mystery of its vanishing act. Unlike pulsars or quasars, which leave behind detectable afterglows, this burst left no trace. No star, no galaxy, no remnant, just silence. Astronomers were floored. The signal was so extreme, some initially questioned if it was even real. Could it have been a glitch, terrestrial interference, a malfunctioning microwave on the observatory grounds? But as more bursts were found, each with that same impossible combination of brevity and brute force, the Lorimer Burst became the Rosetta Stone of a new cosmic mystery. It proved the universe was hiding something extraordinary, transient, cataclysmic events we'd never dreamed of, flashing across the cosmos like interstellar lightning strikes. Yet even now, with hundreds detected, that first enigmatic burst remains a cornerstone, a reminder that sometimes the biggest discoveries come not from looking up, but from digging through the past. What if I told you some fast radio bursts don't just disappear into the cosmic void, they come back? This is where the mystery deepens. While most FRBs are fleeting, one-time events, a handful of them defy expectations by repeating, sending out multiple bursts over days, months, or even years. Take FRB 121102, the first known repeater detected in 2012. Unlike the Lorimer Burst, this one didn't just vanish. It fired off multiple signals from the same patch of sky, sometimes in erratic clusters, other times in eerie, almost rhythmic patterns. Suddenly, the idea that all FRBs came from cataclysmic, one-time explosions like colliding neutron stars or evaporating black holes started to crumble. How could something repeat if it was supposed to be a cosmic death scream? This split between repeaters and one-offs forced astronomers back to the drawing board. One-time FRBs fit neatly into theories involving violent, destructive events, think supernova or magnetar flares, where a single, catastrophic release of energy would explain the burst's intensity and brevity. But repeaters, they demand something far more stable, a source that can survive its own outbursts and fire again. Some scientists now suspect repeater FRBs might originate from highly magnetized neutron stars called magnetars. Picture a spinning stellar corpse, its magnetic field so intense it could strip the electrons from atoms trillions of miles away. Occasionally, these monsters might crack open under the strain, releasing seismic energy that ripples through space as a radio burst. Since the magnetar doesn't destroy itself in the process, it could produce multiple bursts over time, yet even this explanation leaves gaps. Why do some magnetars, if that's truly what's behind repeaters, emit FRBs while others stay silent? And why do certain repeating bursts like FRB 180902 follow such precise intervals, almost like a clock ticking across the cosmos? The more we learn, the clearer it becomes. FRBs aren't just one phenomenon. They might be a cosmic chameleon hiding multiple origins behind the same blinding flash. One-offs could be the death throes of exotic objects we've yet to discover, while repeaters might be the erratic heartbeats of magnetars or even something stranger, cosmic lighthouses powered by technologies beyond our imagination. The existence of repeating FRBs doesn't just challenge our models, it turns them upside down. If some bursts repeat, could all FRBs have the potential to do so, just on timescales longer than we've observed? Or are we dealing with two entirely different cosmic beasts, one that dies in a single, brilliant flash and another that lingers, flickering in the dark? Every new detection raises more questions than answers, pulling us deeper into the enigma. One thing's certain, until we solve the riddle of why some FRBs echo while others fall silent, we're only scratching the surface of this cosmic mystery. Just when astronomers thought fast radio bursts couldn't get any stranger, a revolutionary telescope in Canada turned the field upside down. Enter CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a sprawling, futuristic array of half-pipe antennas nestled in the mountains of British Columbia. Designed originally to map cosmic hydrogen, this unassuming telescope stumbled into FRB research almost by accident, and what it found would rewrite the rules of the game. CHIME's secret lies in its sheer breadth of vision. Unlike traditional radio telescopes that focus on narrow patches of sky, CHIME stares wide-eyed at nearly half the heavens at once. It's like trading a microscope for a panoramic camera, capturing fleeting cosmic events most telescopes would miss. Since it began operating in 2018, CHIME has detected thousands of FRBs, turning what was once a rare, puzzling occurrence into something almost routine. But here's where things get really interesting. Buried in that avalanche of data were patterns no one expected. Take FRB 180916, a repeater that blew minds with its clockwork precision. Every 16.35 days, like cosmic clockwork, it would erupt with bursts for 4 days, then fall silent for 12. This wasn't random static, it was a celestial metronome ticking with a regularity that screamed structure. Then came FRB 121102, another repeater but with a twist. Its bursts arrived in chaotic clusters, like a cosmic Morse code operator hammering out frantic, unpredictable messages. CHIME revealed that some repeaters follow rhythms, while others sputter like faulty engines, challenging the notion that all repeating FRBs play by the same rules. The telescope's unique design also exposed something even more startling. Many FRBs aren't just fleeting whispers, they're polarized. When CHIME analyzed the orientation of these radio waves, it found some twisted in tight spirals, a telltale sign they'd passed through intense magnetic fields. That discovery pointed squarely at magnetars, those hypermagnetic neutron stars, as likely culprits for at least some bursts. Yet even as CHIME data piled up, so did the contradictions. If magnetars were responsible, why did some bursts show polarization while others didn't? And why did a handful of FRBs seem to originate from regions with no known magnetars at all? CHIME didn't just give us more FRBs, it handed us a cosmic jigsaw puzzle. Each new detection added pieces that both fit and clashed with existing theories. The telescope's flood of data revealed that FRBs aren't just rare anomalies. They're everywhere, flashing across the sky at a rate of thousands per day if we could catch them all. Some seem tied to young, star-forming galaxies, while others emerge from quiet, aging neighborhoods of the universe. And then there are the outliers, bursts so energetic or so oddly structured they defy categorization entirely. What CHIME taught us is that fast radio bursts aren't a single mystery, they're a spectrum of enigmas, each with its own quirks and contradictions. The telescope's relentless gaze has turned FRB research from a scavenger hunt into a gold rush, uncovering clues faster than scientists can interpret them. And as CHIME continues to scan the skies, one thing's certain: the next burst it catches might be the one that finally cracks the code, or throws all our theories out the window. Pinpointing the exact origin of a fast radio burst is like trying to find a single blinking firefly somewhere in a pitch-black forest the size of a continent, except that forest is space and the firefly only flashes once. The sheer brevity of FRBs, often lasting just milliseconds, makes them nearly impossible to track in real time. By the time telescopes swing toward the burst's general direction, the signal has already faded into nothingness. Add to that the mind-bending distances these signals travel, and you've got a cosmic needle in a haystack problem on an unimaginable scale. But here's where the story takes a turn. In 2017, astronomers achieved what many thought was impossible. They traced a repeating FRB back to its home. FRB 121102, that enigmatic signal first detected in 2012, was finally linked to a tiny, turbulent dwarf galaxy 3 billion light-years away. This breakthrough didn't just happen by chance. It required a global effort combining data from the world's most powerful radio telescopes, including the Very Large Array in New Mexico and the Arecibo Observatory in Puerto Rico. For the first time, scientists could study not just the burst itself, but the environment that birthed it. What they found was astonishing. This dwarf galaxy was no quiet cosmic backwater. It was a stellar nursery, churning out new stars at a frenzied pace, its skies likely crisscrossed by the violent aftereffects of supernova and the swirling magnetic fields of young magnetars. This chaotic setting fit perfectly with one leading theory, that repeating FRBs might be tied to magnetars, the ultra-dense remnants of exploded stars. But even then, mysteries lingered. Why did some bursts from 121102 arrive with twisted, polarized signals while others didn't? And why, in a galaxy brimming with star formation, was there only one source of these repeating explosions? The localization of 121102 was a watershed moment, proving that FRBs weren't just ghostly echoes, they had real, identifiable homes. Yet for every success, countless bursts remain untraceable. Non-repeating FRBs, which flash once and vanish, are especially elusive. Without the luxury of multiple signals to narrow their origins, these one-off bursts taunt astronomers with their anonymity. Even with cutting-edge tools like the Deep Synoptic Array, which uses hundreds of antennas to triangulate FRB positions, the error margins can still span millions of light years. It's like trying to pinpoint a single lit match on Earth while standing on the Moon. And then there's the sheer variety of host galaxies. Since that first localization, astronomers have traced other FRBs to wildly different environments, some to bustling star-forming regions, others to quiet, aging galaxies where massive stellar explosions are rare. This scattergun distribution hints that FRBs might not have a single, universal origin. Instead, they could be the cosmic equivalent of a multi-tool, produced by different mechanisms in different corners of the universe. One burst might scream from the wreckage of a neutron star collision, while another whispers from the magnetic upheaval of a distant quasar. The challenge now isn't just finding where FRBs come from, it's untangling why they appear where they do, and what their diverse homes reveal about their true nature. Every localized burst is a piece of the puzzle, but the picture they're forming is anything but clear. With each discovery, the universe seems to be telling us that FRBs aren't just mysterious, they're deliberately elusive, as if designed to keep us guessing. And that's what makes them so irresistibly compelling. Among all the cosmic suspects behind fast radio bursts, one stands out: Magnetars, the universe's ultimate magnetic monsters. Picture a neutron star, the collapsed core of a dead star so dense that a teaspoon of its material would weigh 1 billion tons. Now amplify its magnetic field to levels that defy comprehension, quadrillions of times stronger than Earth. These are magnetars, celestial powerhouses capable of bending space itself with their magnetic might. For years, they've topped the list of FRB suspects, but the smoking gun came in 2020 when astronomers witnessed something unprecedented: a fast radio burst erupting from a magnetar right inside our own Milky Way. This game-changing detection happened on April 28, 2020, when a magnetar named SGR 1935+2154, located about 30,000 light-years away, suddenly woke up. As it spewed X-rays and gamma rays, something extraordinary followed: a millisecond radio burst with all the hallmarks of an FRB. Unlike distant bursts from billions of light-years away, this one was in our galactic backyard, allowing telescopes to scrutinize it in unprecedented detail. The match was uncanny: the energy output, the duration, even the twisted polarization of the radio waves pointed to magnetars as at least one source of FRBs. Suddenly, a theory that had been simmering for years had its first direct proof. But here's the twist: while this Milky Way magnetar confirmed that these objects can produce FRBs, it also deepened the mystery in unexpected ways. For starters, the burst was thousands of times weaker than most extragalactic FRBs. If magnetars in distant galaxies are responsible for those more powerful signals, they'd need to unleash energy far beyond what we've seen from local examples like SGR 1935+2154. Could some magnetars be supercharged compared to ours? Or does their environment, like orbiting a black hole or being immersed in a dense star cluster, amplify their outbursts? Then there's the question of variety. The Milky Way's magnetar-produced FRB was a one-time event, lacking the repeating pattern seen in famous cases like 121102. This suggests magnetars might explain some FRBs, but not all. Some scientists speculate that younger, more active magnetars in chaotic star-forming regions could behave differently, firing off repeat bursts as their crusts crack under magnetic strain. Others propose that what we call magnetars might actually be a diverse class of objects with subtypes we haven't even identified yet. The 2020 detection didn't just solve the FRB puzzle, it shattered the illusion that there might be a single, simple answer. Instead, it painted a universe where magnetars, in all their ferocious variety, could be one piece of a much larger cosmic mosaic. Perhaps the most tantalizing clue came from the magnetars' behavior before the FRB. In the hours leading up to the burst, it released a series of X-ray flares, hinting at a build-up of energy before the final, explosive release. This cadence, a crescendo of activity culminating in a radio blast, mirrors patterns seen in some repeating FRBs, suggesting a universal trigger mechanism across different scales. Yet for every connection, gaps remain. Why do some magnetars produce FRBs while others, equally magnetic and violent, show no such signals? Could there be a critical threshold of magnetic field strength or spin rate that tips a neutron star from quiet to FRB producing? And what role does the magnetar's surroundings play? Some theories suggest that debris clouds or plasma around these stars might act like lenses, focusing their explosions into the narrow, intense beams we detect as FRBs. The magnetar link is a breakthrough, but it's also a reminder of how much we still don't know. These objects straddle the line between known physics and the unimaginable, operating in realms where matter and energy behave in ways no lab on Earth can replicate. Every new magnetar-related FRB brings us closer to understanding their role in the grand scheme. But with each answer comes a fresh wave of questions pushing the boundaries of what we thought possible. Long before fast radio bursts entered the cosmic spotlight, another mysterious signal captured the world's imagination, the infamous WOW signal. Detected in 1977 by the Big Ear radio telescope in Ohio, this 72-second burst of radio waves blared from deep space with such intensity that astronomer Jerry Amon scrawled, "Wow." In red ink on the data printout, for decades it stood as the gold standard of unexplained cosmic phenomena, fueling speculation about extraterrestrial origins. But here's where the story twists. FRBs and the WOW signal share more than just their enigma. Both arrived without warning, vanished without trace, and stubbornly resisted conventional explanation. Yet while the WOW signal faded into legend, FRBs have exploded into one of astronomy's most vital fields of study. Why the difference? The answer lies in the evidence or lack thereof. The WOW signal's greatest weakness was its isolation. It happened once, never repeated, and left no breadcrumbs to follow. Without additional detections, astronomers had nothing to compare it to, no way to test hypotheses. Was it a passing comet's reflection, a glitch in the telescope, or, as some dared to hope, a cosmic hello from another civilization? The data stayed silent. FRB, by contrast, refused to stay quiet. As more bursts flooded in, each with similar dispersion patterns, polarization signatures, and energy profiles, their legitimacy as genuine astrophysical phenomena became undeniable. Unlike the WOW signal's lonely cry, FRBs formed a chorus, their sheer numbers allowing scientists to classify them, study their properties, and even trace some back to host galaxies. Repetition turned speculation into science, but the parallels between the two remain haunting. Both signals emerged from the noise as outliers, challenging the limits of human understanding. Both forced astronomers to confront the uncomfortable truth that the universe is far stranger than our textbooks suggest. And both, at their core, represent the thrill of the unknown, the electrifying moment when data defies expectation. The critical difference: technology and timing. The WOW signal arrived in an era before real-time sky surveys and global telescope networks. By the time anyone noticed it, the trail had gone cold. FRB, on the other hand, appeared when the world was watching. Automated systems like CHIME scan the skies incessantly, capturing bursts faster than researchers can analyze them. Machine learning algorithms sift through petabytes of data, flagging anomalies that human eyes might miss. In this new age of discovery, mysteries don't linger in obscurity, they spark revolutions. Yet for all our progress, FRBs still carry that same tantalizing uncertainty that made the WOW signal iconic. Could some bursts, like their legendary predecessor, hold origins beyond natural astrophysics? The possibility, however slim, lingers at the edges of respectable science. But unlike the WOW signal's dead end, FRBs offer a path forward, a way to test, refine, and maybe, just maybe, solve the puzzle. Each new detection chips away at the mystery, revealing clues about the universe's most extreme environments and the forces that shape them. The WOW signal reminds us of how far we've come, while FRBs show us how much further we have to go. Together, they bookend humanity's quest to decipher the cosmos, proving that sometimes the most important answers begin with a signal we don't understand. The sheer energy packed into a single fast radio burst is enough to scramble our understanding of cosmic physics. Picture this: in just a few milliseconds, an FRB can unleash as much energy as the sun radiates over decades. Some extreme bursts, like FRB 190415, clock in at 500 times that, enough to power human civilization for trillions of years if we could harness it. To put that in perspective, if you compressed all the sunlight that falls on Earth over a century into a blink, you'd still fall short of an average FRB's fury. How does something so brief become so powerful? The answer lies in the extreme physics of the universe's most volatile objects. Take magnetars again, those spinning neutron stars with magnetic fields a quadrillion times stronger than Earth. When their crusts buckle under magnetic strain, the resulting starquakes could theoretically generate shockwaves that accelerate particles to near light speeds, converting magnetic energy into a tightly focused radio blast. Think of it like snapping a rubber band, but on a cosmic scale, where the snap rips through space-time itself. Yet even this explanation hits a wall. Magnetar flares, while violent, don't naturally produce the narrow, millisecond-scale pulses we observe in FRBs. To squeeze that much energy into such a fleeting signal, the source would need an almost unnatural precision, like focusing an entire supernova's firepower through a keyhole. Some theorists propose that relativistic jets, similar to those from black holes but far more nimble, might funnel the energy into a coherent beam. Others wonder if cosmic lenses, like clouds of plasma or warped space around neutron stars, act as natural amplifiers, tightening diffuse explosions into the razor-sharp bursts we detect. Then there's the wild card: annihilation events. If certain exotic particles like axions or primordial black holes collided and obliterated each other, their total conversion to energy could match FRB outputs. It's a fringe idea, but the numbers oddly align. Even more speculative are theories involving advanced civilizations. Could a distant society be harnessing black holes or antimatter as cosmic power plants, inadvertently or intentionally broadcasting their breakthroughs across the universe? While there's zero evidence for this, the sheer energy of FRBs forces us to confront how little we know about what's possible in the cosmos. What's clear is that FRBs don't just break the rules, they rewrite them. The laws of physics as we know them struggle to explain how such concentrated energy emerges without obliterating its source. Every detected burst is a paradox, a momentary flicker that outshines galaxies, a whisper louder than a supernova. Until we unravel how nature orchestrates these microscopic explosions of cosmic-scale power, FRBs will remain one of the universe's most dazzling mysteries. A reminder that beyond the calm of our night sky, forces beyond comprehension are at work. Out of the hundreds of fast radio bursts detected, one stands apart not for its power or distance, but for its eerie clockwork precision. FRB 180916 doesn't just repeat, it schedules its outbursts with cosmic punctuality. Every 16.35 days, like celestial clockwork, this burst erupts with radio waves for roughly 4 days, then falls silent for the next 12. It's as if the universe set an alarm, and astronomers were handed the first tangible rhythm in the otherwise chaotic symphony of FRBs. This regularity shattered assumptions. Before its discovery in 2020, most repeating FRBs seemed erratic, some firing off clusters of bursts in hours, others staying quiet for months. But 16.35 days, that's no random interval. It's a number that screams structure, hinting at an underlying mechanism governed by predictable physics. The leading theory, orbital motion. Imagine a neutron star locked in a gravitational dance with another massive object, perhaps a companion star or even a black hole. As it orbits, there might be a specific point where stellar winds, accretion disks, or tidal forces trigger bursts. The 16-day cycle could reflect the time it takes to complete one full orbit, with the active window occurring when conditions align for radio explosions. But here's where it gets thorny. If this were a simple binary system, why would the bursts only fire during 4 specific days? Some researchers suggest the companion object might be shrouded in a thick disk of gas and dust. Only when the neutron star's path takes it through this disk ionizing material or funneling plasma into its magnetic field would the conditions ripen for an FRB. Others propose a wobbling neutron star, its axis slowly precessing like a spinning top. Every 16 days, its magnetic poles might swing into perfect alignment with Earth, beaming radio waves our way like a lighthouse briefly flashing in our direction. Then there's the wild card, magnetar quakes. If the neutron star's crust fractures under magnetic stress at regular intervals, say as it strains against a companion's gravity, those seismic shudders could release energy in predictable waves. Picture a celestial pressure cooker building strain until it has to vent over and over on schedule. But even this elegant idea faces hurdles. No known neutron star in our galaxy behaves this way, and models struggle to explain why the active phase lasts exactly 4 days before abruptly cutting off. The most tantalizing possibility, we're seeing an entirely new class of object. Not just a neutron star, but something more exotic, a hybrid system where extreme magnetic fields, gravitational tides, and plasma physics conspire to create a rhythmic radio beacon. Whatever's behind FRB 180916's precise tempo, it's rewriting the rules. For the first time, we're not just chasing cosmic ghosts, we're tracking a pattern, a rhythm in the chaos. And that might be the key to unlocking FRB's deepest secrets. One of the most puzzling twists in the FRB mystery isn't just where these bursts come from, it's where they don't. Astronomers have spent years perfecting the art of tracing FRBs back to their host galaxies, celebrating each successful localization as a victory. But what happens when you follow the trail of a fast radio burst and find nothing at all? This isn't science fiction, it's reality for a growing number of FRBs that appear to originate from the cosmic void, vast stretches of intergalactic space with no visible galaxies in sight. Are we missing something fundamental, or could these orphan bursts hint at phenomena beyond our current understanding of the universe? Take FRB 150418, a powerful burst detected in 2018. When researchers pointed the Hubble Space Telescope toward its coordinates, expecting to spot a faint, distant galaxy, they were met with darkness, no stars, no gas, not even a trace of the dim dwarf galaxies often linked to repeating FRBs. Just empty space stretching for millions of light years in every direction. At first, scientists assumed the host must simply be too faint for current telescopes, perhaps an ultra-diffuse galaxy, so sparse it barely registers. But even after stacking observations to amplify faint signals, the void remained stubbornly blank. This isn't an isolated case. Multiple FRBs now defy the expectation that every burst must have a galactic home. One theory suggests these orphans might be the cosmic equivalent of intergalactic fireworks explosions from rogue objects wandering the abyss between galaxies. Imagine a hyper-magnetized neutron star, flung from its birthplace during a galactic collision billions of years ago, now drifting alone through the darkness. When it erupts, its bursts travel unimpeded across the void, free from the gas and dust that might obscure their origins. Alternatively, could some FRBs be the echoes of catastrophic events so ancient their host galaxies have long since disintegrated? If a burst occurred during the universe's chaotic early years, its light might only now be reaching us, while the galaxy that birthed it faded into oblivion eons ago. Then there's the more radical possibility. What if these orphan FRBs aren't missing their hosts? What if they never had one to begin with? Some theorists speculate about exotic objects like primordial black holes or cosmic strings, relics from the Big Bang that could lurk unseen in intergalactic space. These objects might generate bursts through mechanisms we've yet to imagine, operating outside the known laws of stellar evolution. Others wonder if the very fabric of space-time could be the source, with quantum fluctuations or dark matter interactions sparking fleeting radio flashes. The implications are staggering. If even a fraction of FRBs truly lack host galaxies, it would mean the universe hides entire populations of objects or processes we've never accounted for. Current telescopes might be blind to their existence simply because we've never thought to look. Upcoming observatories like the Vera Rubin Observatory, with its unprecedented sensitivity to faint, diffuse structures, could finally shed light on these dark corners. Until then, the mystery of the missing host stands as a humbling reminder. For all our cosmic maps and models, the universe still holds blank spots, places where the rules and the players remain unknown. The secret to understanding how far fast radio bursts travel lies hidden in the very fabric of their signals, specifically in a phenomenon called dispersion. When an FRB streaks across the cosmos, it doesn't arrive all at once. Instead, its higher frequency radio waves outpace the lower ones, creating a telltale smear as the burst stretches across milliseconds. This delay isn't a flaw, it's a cosmic breadcrumb trail. The more spread out the signal, the more material it's passed through, meaning dispersion becomes a yardstick for distance. Think of it like shouting through fog. The thicker the fog, the more your voice's deeper tones lag behind the sharper ones. FRBs amplify this effect across billions of light years, with dispersion measures so extreme they reveal journeys through environments we can barely fathom. But the real shock comes from the outliers, bursts with dispersion values that defy logic. Take FRB 190114, with a dispersion measure nearly double that of any other recorded burst. To achieve those numbers, its signal must have traversed not just intergalactic space, but something far denser, perhaps a filament of the cosmic web, those elusive threads of gas and dark matter that weave the universe's large-scale structure. Then there's FRB 180924, whose dispersion suggests it passed through a region so ionized, so turbulent, that no known galaxy or nebula matches its fingerprint. These extreme cases hint at environments astronomy hasn't yet catalogued, vast halos of plasma around galaxy clusters, or the magnetized outskirts of supermassive black holes so distant their host galaxies remain invisible to our telescopes. What's striking is how these dispersion measures clash with the burst's host galaxies when we can find them. Some FRBs originate in relatively calm galactic neighborhoods, yet their signals bear the scars of a journey through what looks like a particle accelerator spanning the cosmos. This paradox has led to wild but plausible theories. Maybe these bursts are being lensed or scattered by invisible structures, dark matter clumps perhaps, or the remnants of primordial quark nuggets left over from the Big Bang. Or consider the possibility that dispersion isn't just a passive toll paid on interstellar highways, but an active signature of the FRB's engine itself. If certain neutron stars are enshrouded in hypermagnetized plasma cocoons, their bursts might emerge already dispersed, mimicking the effect of a much longer journey. The takeaway: dispersion is more than a distance gauge, it's a window into the universe's hidden architecture. Every extreme value challenges our maps of cosmic matter, pushing us to ask, what colossal, invisible landscapes are these signals traversing? And if some FRBs really are modified by environments we've never seen, could they be the key to detecting the undetectable, the dark scaffolding that holds the cosmos together? The answers might be encoded in those milliseconds of delay, waiting for the right telescope, the right algorithm to translate their cosmic whispers. Some fast radio bursts don't just flash, they twist, their radio waves spiraling through space like light filtering through a cosmic prism. This phenomenon, known as polarization, isn't just a visual quirk, it's a smoking gun, revealing the presence of magnetic fields so intense they warp the very fabric of reality. When astronomers analyzed FRB 121102, they found its signal was polarized to an extreme degree, meaning its radio waves weren't just vibrating randomly, they were aligned, forced into order by something with unimaginable magnetic grip. The culprit, likely a Magnetars crushing field trillions of times stronger than Earth's, twisting the burst's light as it escaped into the void. But polarization isn't just about magnetism, it's a forensic tool. The way a burst's polarization changes over milliseconds can map the chaos of its surroundings. Take FRB 200428, whose polarization angle rotated wildly mid-burst. This wasn't just a static field, it suggested the signal had plowed through a turbulent sea of magnetized plasma, perhaps the debris around a newborn neutron star or the swirling outskirts of a black hole's accretion disk. Then there's FRB 180916, whose polarization remained eerily stable, hinting at a cleaner escape path through a more orderly magnetic environment. Each twist and turn in these radio waves paints a portrait of the invisible forces shaping their journey. The real enigma comes when polarization defies expectations. Some bursts, like FRB 190524, show a bizarre circular polarization, a corkscrew pattern that can't be explained by mundane astrophysics. One radical theory points to cosmic strings, hypothetical defects in space-time left over from the Big Bang. If these filaments exist, their gravitational whirlpools could polarize light in ways no known object can mimic. Others speculate about quantum vortices in neutron star interiors, where bizarre states of matter might generate polarization unlike anything we've seen. Even the possibility of exotic compact objects, hypothetical entities like quark stars or prion stars, gets a nod, as their extreme densities could forge magnetic fields in configurations nature shouldn't allow. What makes polarization so revolutionary is its specificity. Unlike distance or energy, which are broad clues, the way an FRB's light is polarized acts like a fingerprint, unique to the environment that shaped it. A burst with a smooth, linear polarization might point to a magnetar born from a clean supernova explosion, while a jagged, irregular pattern could signal a neutron star tangled in the wreckage of a stellar collision. It's as if each FRB carries a tiny imprint of its birthplace encoded in the spin of its radio waves, yet for every pattern decoded, new contradictions emerge. Why do some repeating FRBs lose their polarization between bursts, as if their magnetic prison suddenly vanished? Could certain signals be amplified or altered by passing through regions of space we've yet to map? And what about the bursts with polarization so extreme no known physical process should produce it? The answers might lie beyond our current physics, in the realm of undiscovered particles or forces that operate only in the universe's most extreme crucibles. One thing's certain, when a fast radio burst's light twists, it's not just a curiosity, it's a message written in the language of magnetism and chaos, waiting to be deciphered. Fast radio bursts might be cosmic mysteries, but they're also becoming one of astronomy's most powerful tools. Think of them as interstellar flashlights, their brief but intense beams slicing through the darkness between galaxies. As these signals travel billions of light years, they don't just carry clues about their origins, they pick up fingerprints from every cloud of gas, every wisp of plasma they pass through. And that makes them perfect for solving one of cosmology's biggest puzzles. Where is half the universe's ordinary matter hiding? You'd think accounting for all the atoms in the cosmos would be straightforward, but here's the shocker: when astronomers tally up all the visible stars, galaxies, and gas clouds, they come up short. Roughly half the expected normal matter, what scientists call baryons, is unaccounted for. Not dark matter, not exotic particles, just plain old protons and neutrons that should be there but aren't. The leading theory: these missing baryons are hiding in diffuse, million-degree filaments of gas strung between galaxies, too thin to glow yet too hot to see with conventional telescopes. But catching them in the act requires a radical approach, and that's where FRBs come in. Every burst acts like a cosmic scale. As its radio waves traverse these invisible intergalactic threads, they slow ever so slightly, with lower frequencies lagging behind higher ones, the dispersion effect we discussed earlier. The key insight: the amount of delay directly correlates with how much material the signal has traversed. By measuring dispersion across hundreds of FRBs from different distances, astronomers can essentially weigh the universe's hidden scaffolding. It's like listening to echoes in a cavern. The longer the delay, the more space the sound has crossed, revealing the unseen dimensions around you. Recent studies using CHIME FRB catalog have already delivered tantalizing hints. When researchers analyzed bursts from varying distances, they found dispersion increased in lockstep with how far the signals had traveled, exactly what you'd expect if space between galaxies isn't empty, but threaded with that elusive baryonic fog. Even more compelling, the numbers align with predictions from supercomputer simulations of the cosmic web, those vast, spider-like structures of dark matter and gas that span the universe. But FRBs aren't just confirming theories, they're exposing gaps. Some bursts show more dispersion than expected for their distance, suggesting denser, more turbulent patches of intergalactic material. Others reveal bizarrely smooth regions where space seems emptier than models predict. This variability could map the cosmic web's texture in unprecedented detail, showing where filaments knot together or stretch thin. Future projects like the Square Kilometre Array aim to localize thousands more FRBs, transforming them into pinpricks of light that trace the universe's hidden skeleton in 3 dimensions. The implications stretch far beyond cataloging gas clouds. If FRBs can pinpoint where baryons congregate, they might also reveal how these reservoirs fuel galaxy growth, or why some regions of space seem starved for star-forming material. They could even help solve the missing satellite problem, where simulations predict more dwarf galaxies around giants like the Milky Way than we observe. Perhaps those missing galaxies never formed because their gas was stripped away into these diffuse filaments, detectable only when an FRB's beam grazes them. What's breathtaking is how a phenomenon we barely understood a decade ago is now rewriting the rules of cosmic cartography. FRBs have gone from celestial oddities to precision instruments, letting us weigh the invisible and map the intangible. And as we collect more of these fleeting signals, we're not just solving the mystery of their origins, we're using them to illuminate the darkest, most neglected corners of the universe. The very bursts that defy explanation are becoming the keys to explaining everything else. Fast radio bursts and dark matter have been tangled together in pop science headlines, but the truth is far more interesting and less speculative. While dark matter remains one of the universe's greatest unsolved puzzles, FRBs aren't part of that mystery. They don't emit from some shadowy, invisible substance. They're very much products of the ordinary baryonic matter we can see, or at least detect. The confusion often stems from a simple but misleading overlap. Both dark matter and FRBs are enigmatic, both defy easy explanation, and both involve the word dark in their popular narratives. But that's where the similarities end. Here's the critical distinction. Dark matter neither emits nor absorbs light or radio waves. Its presence is inferred solely through its gravitational pull on galaxies and galaxy clusters. FRB, on the other hand, are dazzling eruptions of electromagnetic energy, bursting across the radio spectrum with unmistakable intensity. They're born from extreme astrophysical processes, magnetars, neutron star collisions, or other high-energy events, all squarely in the realm of visible matter. The irony, FRBs might actually help us study dark matter by mapping the ordinary matter it intertwines with. Every time an FRB signal disperses as it traverses the cosmos, it's essentially weighing the filaments of gas and plasma that dark matter's gravity sculpts into the cosmic web. The misconception likely took root because FRBs feel like dark matter elusive, mysterious, and until recently nearly impossible to trace. But their real value isn't in what they hide, it's in what they illuminate. Take the missing baryon problem we discussed earlier. FRBs act like cosmic divining rods, revealing where ordinary matter pools in the voids between galaxies. Dark matter's gravity likely shaped those pools, meaning FRBs indirectly help us chart the invisible scaffolding of the universe. They're not dark matter's messengers, they're the flashlights we're using to study the structures dark matter builds. Pop science sometimes blurs these lines for dramatic effect, suggesting FRBs could be dark matter particles decaying or colliding, but no credible model supports this. Dark matter candidates, whether WIMP, axions, or something else, don't generate explosive radio bursts. The physics simply doesn't align. What does align is FRB's potential to probe the interface between visible and dark matter. For instance, if an FRB signal bends slightly as it passes through a galaxy cluster, that deflection could hint at the cluster's total mass, including its dark matter halo. In this way, FRBs don't solve the dark matter puzzle directly, but they give us sharper tools to explore its consequences. The takeaway: FRBs are cosmic signposts, not shadowy enigmas. They're helping us refine our maps of the universe's visible architecture while indirectly shining light on the dark matter holding it all together. The next time you see a headline linking FRBs to dark matter, remember, the real story isn't about confusion, it's about collaboration. These bursts are guiding us through the luminous side of the universe's unknowns, one brilliant millisecond at a time. Tracking fast radio bursts would be impossible without the digital archives that compile their chaotic appearances into something resembling order. Enter FRBCat, the Fast Radio Burst Catalog, astronomy's answer to a cosmic detective's case file. Since its launch in 2016, this open-access database has grown from a handful of enigmatic entries to over 1,000 meticulously documented bursts, each tagged with coordinates, dispersion measures, and energy profiles. What started as a scattered collection of oddities has become a treasure trove for pattern recognition, transforming FRBs from random anomalies into a quantifiable population ripe for study. The real power of catalogs like FRBCat lies in their ability to spotlight outliers. When you plot hundreds of bursts on a graph, certain data points leap off the page, like FRB 190418, whose dispersion measure dwarfs all others, or the peculiar repeater FRB 180902 with its metronomic 16-day cycle. These irregularities, obvious only in aggregate, hint at subcategories we might otherwise miss. It's akin to classifying animals. Without a comprehensive catalog, we'd struggle to realize that dolphins and bats both belong to distinct branches of the evolutionary tree. Similarly, FRBCat helps astronomers separate one-off bursts from repeaters, high-energy monsters from their quieter cousins, and polarized signals from unpolarized static. But the catalog's evolution reveals more than just patterns. It maps the explosive growth of FRB science itself. Early entries often lacked precise localizations or host galaxy identifications, reflecting the limitations of pre-CHIME telescopes. Contrast that with recent additions where bursts come bundled with multi-wavelength observations, polarization data, and even ties to specific astrophysical environments like magnetar clusters or starburst galaxies. This granularity turns the catalog into a time capsule, documenting how far our observational tools have advanced in less than a decade. Newer projects are pushing this further. The CHIME/FRB collaboration's live catalog updates nearly in real time, adding dozens of bursts monthly with machine learning-assisted classification. Meanwhile, initiatives like the Deep Synoptic Array's Golden Sample focus on quality over quantity, handpicking bursts with exquisitely precise localizations to probe the universe's large-scale structure. Even amateur astronomers contribute through platforms like the SETI Institute's FRB Candidate Network, where citizen scientists help sift through telescope data for overlooked signals. What's next for FRB catalogs? The answer lies in integration. Imagine cross-referencing FRBCat with gravitational wave alerts or neutrino detectors, creating a multi-messenger alert system that pings astronomers when coincident events occur. Or picture AI-driven databases that predict burst recurrence windows based on historical patterns, turning chance detections into scheduled observations. The catalogs of tomorrow won't just record FRBs, they'll anticipate them, weaving these cosmic flashes into a dynamic, living map of the universe's most elusive phenomena. For now, every new entry remains a potential Rosetta Stone. Whether it's a burst tracing the cosmic web's hidden strands or a repeater defying magnetar models, these catalogs ensure no clue slips through the cracks. They're proof that in astronomy, as in detective work, sometimes the truth isn't in the single spectacular clue, but in the cumulative weight of 1,000 small ones. The idea that fast radio bursts could be signals from an advanced alien civilization isn't just science fiction, it's a hypothesis that once sat squarely on the fringes of mainstream astronomy. When FRBs were first discovered, their bizarre properties, millisecond durations, incomprehensible energy outputs, and seemingly artificial repetition, sparked a tantalizing question: what if we weren't just hearing cosmic static, but the interstellar equivalent of a radio broadcast? The notion wasn't born from wild speculation alone. After all, humanity's own earliest radio transmissions, like the Arecibo message beamed to the stars in 1974, were designed to be brief, high-energy pulses detectable across light years. Could FRBs be someone else's version of a cosmic hello? For a brief moment, the possibility felt almost plausible. Some repeating bursts, like FRB 121102, emitted patterns that seemed too structured to ignore, clusters of signals arriving in rhythms that mirrored mathematical sequences. Others, like the infamous Lorimer Burst, arrived with such concentrated energy that theorists speculated about directed propulsion systems, perhaps alien megastructures harnessing black holes or antimatter to power interstellar beacons. Even the great Stephen Hawking mused that FRBs might warrant scrutiny under SETI umbrella, given their unexplained intensity and fleeting nature. The allure was undeniable. Here was a phenomenon that defied every natural explanation, and in that gap of understanding, imagination flourished. But science thrives on Occam's razor, the principle that the simplest explanation, requiring the fewest assumptions, is often correct. And as FRB detections multiplied, the alien hypothesis began to unravel. First, the sheer volume of bursts became a problem. With thousands occurring across the sky daily, the energy required for an extraterrestrial civilization to power such a vast beacon network would exceed anything remotely plausible, even for a Kardashev Type II society harnessing an entire star's output. Second, the polarization data didn't lie. The twisted radio waves pointed unambiguously to extreme magnetic environments, like those around magnetars rather than artificial transmitters. Finally, the coup de grace came when astronomers traced multiple FRBs to cataclysmic events, like the Milky Way's own magnetar eruption in 2020. If these bursts could originate naturally in our backyard, why invoke aliens for those farther away? Yet dismissing the idea entirely misses why it captivated us in the first place. FRBs embody the same existential curiosity that drives SETI, the hope that we might not be alone. Technosignatures, the detectable traces of advanced civilizations, remain a legitimate field of study, even if FRBs aren't among them. Projects like Breakthrough Listen still scour repeating FRBs for embedded patterns, just in case. It's a reminder that science progresses by questioning everything, even its own assumptions. The alien hypothesis, though debunked, served a purpose. It pushed astronomers to seek extraordinary evidence for extraordinary claims, and in doing so, uncovered truths far stranger than fiction. What's left is a paradox. FRBs are more fascinating as natural phenomena than they ever were as alien signals. Their true origins, neutron stars cracking under magnetic strain, black holes shredding companion objects, or whatever else we've yet to discover, reveal a universe more violent and inventive than we dared to imagine. But the dream of contact lingers, not in the bursts themselves, but in the questions they inspire. If something as simple as a spinning stellar corpse can mimic an interstellar beacon, what else might we be misinterpreting? The search continues, not for aliens in the static, but for the next cosmic riddle waiting to upend our understanding all over again. Of all the repeating fast radio bursts, FRB 190520 stands out for something utterly bizarre. It never truly goes dark. Unlike other repeaters that flash intermittently against the silent backdrop of space, this one lingers, emitting a faint but persistent radio glow even between its explosive bursts. It's as if someone left a cosmic nightlight on, a steady hum beneath the fireworks. This strange behavior has astronomers scrambling for explanations because it challenges everything we thought we knew about how these bursts are powered. The leading theory, FRB 190520, might be a newborn magnetar, still swaddled in the turbulent cradle of its birth. When massive stars die in supernova, their collapsed cores, now neutron stars often find themselves surrounded by a nebula of debris, a swirling cloud of gas and dust expelled in the explosion. If the neutron star happens to be a magnetar, its unimaginably strong magnetic field could interact with this nebula, creating a constant source of radio waves. Think of it like a lighthouse, not just flashing its beam, but also keeping its floodlights on 24/7. The bursts would come from the magnetar's occasional seismic tantrums, while the steady glow arises from the nebula's charged particles spiraling around its magnetic field lines. But there's a twist. Most magnetars we've observed in our galaxy don't have persistent radio sources like this, which raises the question, is FRB 190520 unusually young? Some models suggest that in the first few decades after a supernova, a magnetar's surroundings are still dense enough to fuel this constant emission. As the nebula disperses over centuries, the glow would fade, leaving behind only the sporadic bursts we see from older magnetars. If true, that makes this FRB a rare glimpse into a magnetar's tumultuous infancy, caught in a fleeting phase of its life. Not everyone's convinced, though. Alternative ideas range from a magnetar orbiting a companion star, whose stellar wind feeds the persistent emission, to more exotic scenarios involving failed supernova or even quark stars, hypothetical objects even denser than neutron stars. The wild card, the glow's brightness doesn't quite match predictions for a simple nebula, hinting that something stranger might be at play. What makes this mystery so compelling is that it bridges two cosmic enigmas. FRB 190520 isn't just a fast radio burst, it's a laboratory for extreme physics, a chance to study how magnetars evolve and how their surroundings shape their signals. Every new observation peels back another layer, revealing just how much we still don't understand about these cosmic powerhouses. And with each unanswered question, the universe reminds us that even its most fleeting flashes can leave behind clues that echo for millennia. One of the most enduring analogies for explaining repeating fast radio bursts is the cosmic lighthouse, a spinning neutron star sweeping beams of radiation across space like the rotating light atop a coastal tower. The idea seems elegant at first glance. Just as Earth only sees a lighthouse's flash when the beam swings our way, we'd only catch an FRB when the neutron star's emission cone briefly points at us. This model neatly accounts for the regularity of some repeaters, like FRB 180916's 16-day cycle, which could reflect the time it takes for the star to complete one full rotation or precession. But the lighthouse analogy starts creaking under scrutiny. For one, neutron stars spin fast, some completing hundreds of rotations per second. If FRBs were tied directly to their spin, we'd expect bursts arriving in milliseconds or seconds, not days or weeks. To explain the observed gaps, theorists have proposed elaborate modifications. Maybe the beam isn't fixed to the star's rotation but wobbles like a spinning top, or perhaps it's the orbit of a companion star that periodically tilts the beam into view. Others suggest the bursts don't come from the neutron star itself, but from a swirling disk of debris around it, with clumps of material sparking radio waves only when they collide at specific orbital phases. The biggest flaw in the lighthouse model, it can't explain why some FRBs erupt in erratic clusters while others follow perfect rhythms. If a spinning neutron star's beam were the sole factor, every repeater should display clockwork regularity, yet many, like FRB 121102, fire off bursts in chaotic fits and starts. This inconsistency hints that something far more dynamic is at play, perhaps magnetic reconnection events, sudden rearrangements of the star's field lines that occur unpredictably like solar flares. Then there's the energy problem. Lighthouse beams from known pulsars are steady and persistent, whereas FRBs are explosive and transient. To reconcile this, some researchers propose giant pulse theories, where neutron stars occasionally emit bursts 1,000,000 times brighter than normal. But even these extreme pulses pale next to the energy of an FRB, which can outshine its host galaxy. The lighthouse model also struggles with polarization data. Many FRBs show radio waves twisted into complex spirals, suggesting they've traversed incredibly turbulent magnetic fields far messier than the orderly beams we see from typical pulsars. Perhaps the most telling critique comes from magnetar observations. When our own galaxy's magnetars flare, their radio bursts look nothing like lighthouse beams. They're jagged, asymmetric, and often accompanied by X-ray fireworks. If magnetars are indeed the source of some FRBs, their emissions may be less like a rotating spotlight and more like a strobe in a hurricane, flashing chaotically amid a maelstrom of magnetic violence. This isn't to say the lighthouse idea is worthless, it's a stepping stone, a simplified framework that helped astronomers start piecing together the puzzle. But as FRB data grows more nuanced, so must our models. The truth likely lies somewhere between order and chaos, where spinning neutron stars, magnetic mayhem, and unseen companions conspire to create bursts that dazzle us with their complexity. The lighthouse may guide our first steps, but the real story is unfolding in the storm. At first glance, fast radio bursts and gamma-ray bursts seem like cosmic opposites, one a fleeting whisper in radio waves, the other a blinding scream of high-energy light. But dig deeper and tantalizing connections emerge, suggesting these two phenomena might be distant cousins in the universe's family of extreme events. The most compelling link comes from a rare class of gamma-ray bursts called short GRBs, which last less than 2 seconds and are thought to arise from collisions between neutron stars. These mergers don't just unleash gamma rays, they're also predicted to generate powerful, millisecond-long radio bursts as debris slams into surrounding material at near-light speeds. Take GRB 205-22216, detected in 2021. This short GRB, originating from a neutron star merger over 1 billion light-years away, was followed by something unprecedented, a rapid, localized radio flash bearing all the hallmarks of an FRB. While not identical to classic fast radio bursts, this signal's timing and energy profile aligned eerily with theoretical models predicting FRB-like emission from post-merger magnetars or hypermassive neutron stars. The implication, some FRBs might be the radio afterglow of these cataclysmic collisions, the quieter echo of a gamma-ray cataclysm, but the plot thickens. Not all potential FRB-GRB pairings fit this tidy narrative. Another event, GRB 1909294, showcased a long-duration gamma-ray burst typically associated with collapsing massive stars coinciding with a peculiar radio transient. Unlike the clean neutron-star merger scenario, this pairing defies easy classification. Could certain supernova produce both GRBs and FRBs under rare conditions? Some theorists speculate that supernova shocks plowing into dense stellar winds might generate overlapping emissions, while others point to newly born magnetars, whose birth throes could unleash both gamma and radio fury. The similarities don't end there. Both FRBs and GRBs exhibit afterglows, persistent emission fading over days or weeks, though in different wavelengths. GRBs light up in X-rays and visible light, while some FRBs leave trace radio signatures. This parallel hints at shared environments like turbulent magnetar nebulae or black hole accretion disks capable of sustaining multi-wavelength aftermaths. Even their dispersion measures tell a story. Just as FRB signals get stretched by interstellar gas, GRB afterglows show frequency-dependent delays, suggesting both phenomena pierce similar cosmic landscapes. Yet for every correlation, contradictions arise. Most FRBs lack any detectable GRB counterpart, and the vast majority of gamma-ray bursts show no accompanying radio burst. This mismatch could mean the two are fundamentally different beasts, or that we're missing key pieces of the puzzle. Perhaps FRB-producing GRBs require specific conditions, a particular magnetic field alignment, a precise viewing angle, or a neutron star with just the right spin. Alternatively, the radio bursts might be drowned out by the GRB's brilliance unless observed with specialized instruments, the most radical possibility. That FRBs and GRBs aren't direct siblings but products of the same cosmic engine operating in different modes. Imagine a magnetar's magnetic field snapping like a rubber band. Sometimes it unleashes a focused radio beam, an FRB. Other times it triggers a broader gamma-ray cascade, a GRB, depending on how and where the energy releases. This duality could explain why some events, like the Milky Way's magnetar flare in 2020, produced both an FRB and X-ray burst, two sides of the same explosive coin. What's clear is that the FRB-GRB connection, however tentative, forces us to reconsider the boundaries of high-energy astrophysics. These phenomena might not be isolated curiosities, but threads in a larger tapestry of cosmic violence, woven together by the universe's most extreme physics. Every coincident detection and every puzzling mismatch sharpens our understanding of how matter behaves under conditions no lab could ever replicate. The hunt for more overlapping events isn't just about solving two mysteries, it's about discovering if they were ever truly separate to begin with. Most fast radio bursts scream across the high-frequency radio spectrum, but where are their deeper, lower-pitched counterparts? This missing chorus of low-frequency FRBs presents one of the field's quietest puzzles. While observatories like CHIME routinely catch bursts between 400 and 800 MHz, detections below 200 MHz remain vanishingly rare. It's as if the universe has turned down the bass, leaving astronomers straining to hear the full cosmic symphony. The prime suspect behind this scarcity lies in the interstellar and intergalactic plasma that permeates the cosmos. As FRBs travel billions of light-years, their lower frequency waves interact more strongly with free electrons in this diffuse medium, a process called free absorption. Picture sunlight filtering through murky water. Just as the longer red wavelengths penetrate deeper while blues scatter, low-frequency radio waves get progressively dampened as they plow through ionized gas. For extremely distant bursts, this absorption can completely erase frequencies below about 300 MHz before they ever reach our telescopes. Even nearby FRBs face hurdles, as our own Milky Way's turbulent plasma clouds act like radio fog, further obscuring the lowest frequencies. But plasma absorption isn't the only culprit. Some FRBs might inherently lack strong low-frequency emission due to their production mechanism. Take the coherent curvature radiation model, where charged particles surf along neutron stars' twisted magnetic field lines. This process naturally favors higher frequencies, like how a tightly coiled whip cracks with a sharp snap rather than a low rumble. Similarly, if bursts arise from shock fronts in magnetar winds or neutron star collisions, the physics of those abrupt energy releases could preferentially generate waves at gigahertz frequencies while leaving the radio spectrum's basement dim. The few low-frequency FRBs we have detected only deepen the enigma. FRB 180117, captured at 140 MHz by the LOFAR telescope, displayed bizarre spectral features. Its signal was fragmented, as if shredded by propagation through an invisible cosmic grater. Meanwhile, tentative detections by the Murchison Wide Field Array suggest some bursts might actually peak at frequencies below 100 MHz, challenging assumptions about their emission mechanisms. These outliers hint that FRBs could occupy multiple niches across the radio spectrum, with distinct populations hiding just beyond our current observational limits. New telescopes are turning up the volume on this mystery. The upcoming Square Kilometre Array's low-frequency component promises to scour the sub-300 MHz range with unprecedented sensitivity, while targeted campaigns by arrays like LOFAR aim to catch more ultra-low-frequency bursts. Every detection or absence rewrites the rules. If the scarcity holds, it could confirm that FRBs are fundamentally high-frequency phenomena, shaped by physics that mutes their deeper voices. But if more low-frequency bursts emerge, they might reveal entirely new classes of sources lurking in the static, waiting for the right instruments to tune into their wavelength. Among the many theories trying to crack the fast radio burst enigma, one of the most intriguing and underappreciated is the cosmic comb model. Picture a neutron star spinning at dizzying speeds, its magnetic field whipping charged particles into a frenzy as they race outward at near light speed. Now imagine a shock wave plowing through this stellar wind like a truck hitting a traffic jam, forcing those particles into sudden, violent collisions. The result, a spectacular burst of radio waves focused into a narrow beam by the neutron star's crushing magnetic field. This shockwave-driven mechanism, dubbed the comb model, offers a fresh twist on FRB origins, one that sidesteps some of the thorniest problems plaguing more popular theories. Unlike magnetar flares or neutron star collisions, which rely on cataclysmic one-time events, the cosmic comb scenario suggests FRBs could be routine byproducts of neutron star physics. The key lies in the chaotic environment around these spinning corpses. As particles in the stellar wind slam into the shockwave, their sudden deceleration generates coherent radio emission, similar to how a lightning bolt's rapid acceleration of electrons creates thunder. But here's the kicker: because the neutron star's magnetic field acts like a cosmic lens, the burst becomes highly directional, explaining why we only catch FRBs when the beam sweeps across Earth. It's a process that could operate continuously, with shockwaves rippling through the wind whenever denser plasma clouds or magnetic disturbances pass by. What makes this model stand out is its ability to explain both repeaters and one-offs without invoking exotic scenarios. A stable shockwave structure, perhaps caused by a companion star or debris field, could produce regular bursts like clockwork, fitting neatly with the 16-day cadence of FRB 180916. Meanwhile, erratic shockwaves from turbulent plasma clumps might account for the irregular repeaters, and isolated shocks from passing asteroids or stellar flares could generate one-off bursts. Even polarization finds a natural explanation. The neutron star's magnetic field would imprint its signature on the escaping radio waves, matching the twisted patterns observed in many FRBs. Yet the cosmic comb isn't without its skeptics. Mainstream magnetar models still dominate, partly because we've seen Milky Way magnetars produce FRB-like bursts. The comb's Achilles heel: we've never directly observed the shockwaves it depends on, at least not around neutron stars known to be FRB sources. Detecting these subtle structures would require exquisitely sensitive radio imaging, something next-gen telescopes like the next-generation Very Large Array aim to provide. There's also the energy problem. While the comb neatly explains moderate bursts, the most extreme FRBs, like the record-breaking FRB 190415, might still demand the raw power of a magnetar's magnetic field snapping like an over-twisted rubber band. The beauty of the cosmic comb lies in its versatility. It doesn't replace other theories so much as complement them, offering a middle path where FRBs emerge from the ordinary turbulence of neutron star life rather than rare apocalyptic events. Perhaps some bursts arise from magnetar tantrums while others spark from shockwaves, a cosmic diversity that would explain why no single model fits all observations. As telescopes uncover more FRBs with hybrid traits, this underdog idea might yet prove its worth, revealing that sometimes the universe's most dazzling flashes come not from its grand explosions, but from the everyday collisions in its darkest storms. Among the wilder theories swirling around fast radio bursts, few spark as much imagination or skepticism as the idea that these cosmic flashes might be glimpses of time itself unraveling. Some fringe physicists and science fiction enthusiasts have proposed that FRBs could be echoes of events yet to happen, their radio waves tunneling backward through time like ripples moving upstream. Others take it further, suggesting these bursts might be emissions from white holes, the hypothetical time-reversed twins of black holes spewing matter and energy into our universe from some unseen dimension. It's a dizzying concept, blending advanced general relativity with speculative cosmology, but here's the catch: there's not a shred of empirical evidence to support it. The time travel angle stems from a quirky feature of Einstein's equations, which mathematically permit solutions where space-time curves so severely that cause and effect flip. In theory, under extreme conditions like those near a spinning black hole's ergosphere, light could follow a closed time-like curve, effectively looping back to an earlier moment. If an FRB originated in such a warped region, its signal might arrive before the event that created it, at least on paper. The white hole hypothesis leans on another abstract idea, that black holes, as they evaporate via Hawking radiation, might transform into their theoretical opposites, violently ejecting everything they once swallowed. But while these notions make for thrilling thought experiments, they collide with observable reality. No known FRB shows the telltale signatures, like reversed entropy or blue-shifted echoes, that would hint at retrograde causality. And white holes, they've never been detected, existing only as ink on theorists' notepads. That hasn't stopped the speculation from flaring around certain peculiar bursts. FRB 190110, with its bizarre double-peaked structure, had some enthusiasts whispering about time-lagged duplicates, as if the same event had somehow broadcast twice, with the second pulse traveling a longer, time-bent path. A more prosaic explanation, involving lensing by an intervening plasma cloud, eventually fit the data better. Similarly, the precise repetition of FRB 180916's 16-day cycle led to playful musings about cosmic alarm clocks set by future civilizations. The truth, as always, proved less sensational but no less fascinating are orbital mechanics around a neutron star binary. What makes these fringe ideas worth addressing, if only to debunk, is how they reflect our hunger for the extraordinary. FRBs are so inherently strange that they invite radical explanations, but science thrives on testable predictions, and so far, every time travel or white hole claim crumbles under scrutiny. The dispersion measures, polarization patterns, and host galaxy associations of FRBs all align with natural astrophysical processes, not paradoxes. Even the burst's sheer energy, while staggering, fits comfortably within the limits of magnetar physics or neutron star collisions. Yet there's value in the speculation, if only as a reminder of how much we still don't understand. The fact that FRBs can inspire such creative theories speaks to their power as cosmic riddles. They push us to the edge of known physics, where the line between bold hypothesis and pure fantasy blurs, while the evidence overwhelmingly points to magnetars, shockwaves, and other natural phenomena. The allure of the unknown lingers. Perhaps the real magic of FRBs isn't that they're messages from the future, but that they keep us asking questions that feel just as futuristic. Plasma, the fourth state of matter, might be the invisible sculptor shaping fast radio bursts into the bizarre signals we detect. Imagine a neutron star shrouded in a seething fog of ionized particles, their chaotic dance dictated by magnetic fields strong enough to bend atoms into submission. As an FRB's radio waves tear through this electrified haze, they don't emerge unscathed. The plasma leaves its fingerprints, twisting the signal's polarization, smearing its frequencies, and sometimes even splitting it into multiple echoes. This isn't just interference, it's a cosmic laboratory, revealing conditions so extreme they defy Earth-bound physics. Take magnetars, those neutron stars with magnetic fields 1,000 trillion times stronger than Earth. Their magnetospheres are essentially oceans of plasma, where electrons spiral along field lines at near light speeds. When an FRB erupts from such an environment, the plasma acts like a hall of mirrors, reflecting and refracting the radio waves until they bear little resemblance to their original form. Some bursts, like FRB 200428, show wild polarization swings mid-burst, evidence of the signal plowing through a swirling plasma vortex, perhaps a magnetar's turbulent wind or the debris of a recent starquake. Other FRBs exhibit subbursts, where the main signal fragments into smaller pulses, as if the plasma cloud tore it apart like light passing through frosted glass. But plasma's influence doesn't end at the source. Even after escaping the magnetosphere, FRBs must traverse the interstellar and intergalactic medium, a diffuse but ever-present plasma soup. This is where dispersion comes into play, the process that stretches lower-frequency radio waves into a cosmic yawn. The more plasma an FRB traverses, the more its signal spreads, creating that telltale smear across milliseconds. Yet some bursts, like FRB 190418, show dispersion measures so extreme they imply passage through regions denser than standard intergalactic space. Could these be threading through remnants of ancient supernova, expanding bubbles of plasma left behind by stellar explosions? Or perhaps they've grazed the outskirts of galaxy clusters, where superheated gas pools in gravitational wells, its plasma content far higher than the cosmic average. The most tantalizing clues come from repeating FRBs. If plasma around the source were static, we'd expect each burst to look identical. Instead, repeaters like 121102 show dramatic variations in polarization and structure between bursts, suggesting their surrounding plasma is alive, shifting, reconnecting, or even boiling away over time. One theory posits that magnetars might be orbited by asteroid belts or cometary clouds, their icy bodies vaporizing into plasma as they plunge into the star's magnetic grip. Each new collision would temporarily alter the plasma density, twisting subsequent bursts in unique ways. Plasma doesn't just obscure FRBs, it illuminates them. By decoding how these signals are distorted, astronomers can map the invisible architecture of their birthplaces. A burst's polarization might trace the helical twist of a magnetar's field lines, while its spectral breaks could reveal the temperature and density of intervening plasma clouds. It's like listening to a song played through a wall. The distortions tell you something about the wall itself. Future telescopes, like the Square Kilometre Array, aim to dissect these distortions with unprecedented precision, turning FRBs into probes for the universe's most elusive plasma structures. What's emerging is a realization that without plasma, FRBs might not exist at all. Some models suggest the bursts themselves are born from plasma instabilities, shockwaves in magnetar winds, or cascading particle avalanches in neutron star magnetospheres. In this view, plasma isn't just a passive filter, it's the engine, the canvas, and the lens all at once. And as we peel back its layers, we're finding that the most mysterious thing about fast radio bursts might not be the bursts themselves, but the electrified labyrinths they must navigate to reach us. Among all the host environments linked to fast radio bursts, none has baffled astronomers quite like the ancient, serene realm of globular clusters until FRB 2020-0120E shattered expectations. Nestled inside Messier 81's globular cluster, a densely packed sphere of stars nearly 12 billion years old, this burst defies every assumption about where FRBs should originate. Globular clusters are cosmic retirement homes, filled with elderly stars so stable and quiet that explosive events like supernova and the magnetars they spawn should be vanishingly rare. Yet here we are, detecting an FRB from a place where theory says it shouldn't exist. What makes this detection so perplexing? First, consider the stellar demographics. Globular clusters formed during the universe's wild youth, and their stars burned through their fuel eons ago. Today, they're dominated by calm, cooling white dwarfs and leisurely pulsars, not the volatile young magnetars thought to power most FRBs. For a burst to emerge here, either our understanding of magnetar formation is incomplete, or we're glimpsing an entirely new engine behind these cosmic flashes. One tantalizing possibility, a blitzar, a neutron star that narrowly avoided collapsing into a black hole during its birth. Such an object, spinning furiously and encased in a fossil magnetic field, could lurk in these clusters, occasionally unleashing bursts without the fireworks of a recent supernova. Then there's the exotic binary scenario. Imagine a neutron star locked in a tight orbit with a white dwarf or another compact object. As they spiral closer over millennia, tidal forces or magnetic interactions could trigger sporadic energy releases, effectively turning the pair into a cosmic flint, striking sparks across the radio spectrum. Alternatively, the burst might trace back to a primordial black hole, one of those hypothetical relics from the Big Bang, as it evaporates or interacts with the cluster's dense stellar environment. These far-flung ideas underscore how deeply FRB 2020-0120E has disrupted the status quo. The implications ripple outward. If magnetars can form in globular clusters, it suggests pathways we've overlooked, perhaps through white dwarf collisions or the delayed collapse of ultra-dense remnants. Even more provocative is the idea that this burst represents a separate class of FRB altogether, one divorced from the cataclysmic origins we've come to expect. Its very existence forces us to expand the playing field, to consider that the universe might be crafting these brilliant flashes in environments we'd written off as peaceful. As telescopes continue monitoring this enigmatic repeater, one thing is certain: its whispers from the cosmic past are rewriting the rules. Whether it's a freak occurrence or a signpost to undiscovered astrophysics, FRB 2020-0120E proves that when it comes to fast radio bursts, the universe still holds surprises in its oldest corners. Every fast radio burst we've ever detected is likely just the tip of a cosmic iceberg, the loudest, brightest outliers in a sea of whispers too faint for our telescopes to catch. This invisible threshold, known as the FRB wall, represents the observational limit beyond which countless bursts slip through undetected. they're radio murmurs lost in the static of the universe. The implications are staggering. For every FRB we observe, there could be dozens, even hundreds more that never register on our instruments, each one a missed opportunity to decode these cosmic enigmas. The math behind this detection gap is sobering. Consider CHIME, currently the most prolific FRB hunter, which detects bursts at a rate of about 1 per day. Yet models of neutron star populations and magnetar activity suggest the true rate could exceed 10,000 FRBs per day across the entire sky. Why the discrepancy? It all comes down to sensitivity and distance. The farther a burst travels, the more its signal disperses and weakens, fading below the noise floor of even our best receivers. Most FRBs likely originate in distant galaxies, their signals stretched and diluted by billions of light-years worth of cosmic expansion and interstellar plasma. By the time they reach Earth, only the most cataclysmic, those with energies dwarfing our sun's output for decades, still pack enough punch to stand out. This bias skews our entire understanding of these phenomena. We're effectively studying the universe's megaphones while ignoring its whispers. Take FRB 190415, the most energetic burst ever recorded. It was 500 times more luminous than a typical FRB. If such extreme outliers dominate our catalogs, we might be missing a hidden population of softer, more frequent bursts that could reveal entirely new categories of sources. Imagine if hurricane researchers only studied Category 5 storms. Their understanding of cyclones would be dangerously incomplete. Similarly, our view of FRBs is disproportionately shaped by the cosmic equivalents of super typhoons, leaving quieter but equally important weather patterns unexplored. The FRB wall also distorts our grasp of burst diversity. Repeaters like 121102 dominate headlines because their recurring nature makes them easier to study. But are they truly representative, or just the low-hanging fruit in an orchard of unseen varieties? Some theorists speculate that faint, ultra-frequent FRBs could exist, perhaps tied to less violent processes like the steady flickering of old magnetars or the gentle mergers of white dwarfs. Others envision a continuum of energies where the bursts we see are merely the tip of a vast distribution extending down to energies so low they blend into the background hum of the cosmos. Breaking through this wall requires telescopes of unprecedented sensitivity. The upcoming square-kilometer array, with its millions of antennas spread across 2 continents, aims to push detection thresholds 100-fold deeper, potentially unveiling this hidden population. Meanwhile, projects like DSA 2000 will scan the sky with such precision that even FRBs from the universe's earliest epochs, currently lost in the fog of cosmic dawn, might finally flicker into view. Every step toward greater sensitivity doesn't just add to our FRB tally. It redefines what these bursts are, revealing whether the ones we know represent the rule or the exception. The most humbling realization: we've spent years marveling at FRBs as rare, exotic events, when in truth, the cosmos might be crackling with them constantly, a cacophony of radio flashes we're only now learning to hear. The FRB wall isn't just a technical hurdle. It's a mirror reflecting how much of the universe's language still slips through our fingers, unheard and untranslated. And that's perhaps the greatest mystery of all, not the bursts we detect, but the countless ones we don't. Imagine catching a fast radio burst erupting from distant space at the exact same moment a ripple in space-time reaches Earth, or a ghostly neutrino streaks through our detectors. These simultaneous events, if we could confirm them, would revolutionize our understanding of FRBs, tying them directly to the universe's most violent collisions. This is the promise of multi-messenger astronomy, using not just light but gravitational waves, neutrinos, and cosmic rays to piece together the full story behind these bursts. The challenge: these signals travel billions of light years across a chaotic cosmos. and getting their arrival times to line up is like trying to sync fireworks exploding in a hurricane. The most tantalizing potential partners for FRBs are gravitational waves, the faint tremors in space-time caused by cataclysmic events like neutron star mergers. When LIGO detected its first neutron star collision in 2017, astronomers scoured the skies for accompanying electromagnetic signals, finding everything from gamma rays to kilonavy. But no definitive FRB emerged despite theories predicting their possible connection. The absence wasn't necessarily a deal breaker. FRB beams are narrow, and Earth might simply have been outside the emission cone. Still, the hunt for coincident detections intensified, fueled by the prospect that some FRBs could be the electromagnetic counterparts to gravitational wave events too distant or faint for LIGO to pinpoint alone. Neutrinos add another layer of intrigue. These nearly massless particles, born in the hearts of supernova or around black holes, travel unimpeded through cosmic dust and gas. If an FRB source, say, a flaring magnet, also blasted out high-energy neutrinos, catching both signals would offer a direct window into the explosion's core physics. IceCube, the neutrino observatory buried in Antarctic ice, has scanned the skies for years, hoping to spot a neutrino in concert with an FRB. In 2020, a flicker of excitement arose when a neutrino candidate appeared roughly coincident with a repeating burst from FRB 180902. But the association remained speculative. Without tighter timing or directional alignment, it could have been a cosmic coincidence. The logistical hurdles are immense. Gravitational wave detectors like LIGO and Virgo have wide error margins, sometimes spanning hundreds of square degrees on the sky, a vast haystack for finding an FRB needle. Neutrino observatories face similar challenges, with directional precision often too coarse to definitively link a neutrino to a specific burst, even when signals align roughly in time and space. Proving they're connected requires statistical heavy lifting. Researchers must calculate the odds that such an overlap could happen randomly, a process complicated by the sheer number of FRBs and high-energy particles constantly raining down on Earth. Yet the potential payoff keeps telescopes and detectors on high alert. Projects like AMON, the Astrophysical Multi-Messenger Observatory Network, now aggregate real-time alerts from gamma-ray satellites, neutrino detectors, and FRB hunters, using machine learning to flag possible correlations. The DREAM, a singular event where an FRB, gravitational wave, and neutrino all arrive within milliseconds, pinpointing a neutron star collision or magnetar flare with unprecedented precision. Such a detection could reveal not just the engine powering FRBs, but also the inner workings of extreme physics, how matter behaves under conditions so intense they warp the fabric of reality. Until then, each near miss teaches us something new. The absence of coincident detections so far suggests that if FRBs are tied to gravitational waves or neutrinos, the relationship isn't straightforward. Maybe only a subset of bursts, those from particularly violent mergers or hypermagnetized environments, produce multi-messenger signals. Or perhaps we're seeing the limits of our current technology, needing sharper instruments to catch the whispers of these cosmic convergences. One thing's certain, in the quest to decode FRBs, every messenger light, gravity, or particle brings us closer to the truth, even when they arrive alone. Picture the aftermath of a supernova, a titanic explosion that leaves behind a neutron star, its newborn core surrounded by a swirling maelstrom of debris. Most of that debris escapes into space, but some of it, pulled by gravity, comes crashing back down in a violent rain of metal and gas. This supernova fallback isn't just cosmic recycling. It could be the engine behind some of the universe's most powerful fast radio bursts. Here's how it works. When a massive star explodes, the outer layers blast outward at thousands of kilometers per second, but the inner regions collapse into an ultra-dense neutron star. In the chaotic hours and days that follow, some of that ejected material, particularly heavy elements like iron and nickel, finds itself trapped in the neutron star's gravitational grip. As this fallback material plummets back toward the surface, it doesn't land gently. Instead, it slams into the neutron star's magnetosphere at relativistic speeds, releasing staggering amounts of energy. The impact is like an avalanche of white-hot shrapnel hitting a steel wall, except here, the wall is a magnetic field strong enough to distort atoms, and the avalanche is carrying enough kinetic energy to outshine galaxies. The supernova fallback model offers elegant solutions to some of FRBs' biggest mysteries. First, it explains their extraordinary energy. A single chunk of fallback debris, no larger than a mountain but traveling near light speed, could deliver enough punch to power an FRB all on its own. Second, it accounts for both one-off bursts and repeaters. An initial wave of fallback might produce a single cataclysmic FRB, while residual material, clumps lingering in unstable orbits, could trigger repeat bursts as they intermittently collide with the neutron star over years or centuries. Even polarization fits neatly. The neutron star's magnetic field would twist the radio emission into the spiraling patterns we observe, but the model has its skeptics. One major hurdle is timing. Fallback is thought to peak within days or weeks of a supernova, yet many FRB host galaxies show no signs of recent star formation, meaning their neutron stars could be millions of years old. Could fallback really linger that long? Some theorists suggest delayed mechanisms, like the slow in-spiral of an asteroid belt or the late-stage collapse of a debris disk, but these ideas stretch the limits of current simulations. Another challenge is the lack of accompanying X-rays. Fallback impact should heat the neutron star's surface enough to produce bright X-ray flares, yet most FRBs show no such counterparts. Despite these gaps, the fallback model gains credibility from its flexibility. Unlike magnetar flares, which require highly specific magnetic field configurations, fallback could happen to any young neutron star with sufficient debris nearby. It also dovetails with observations of some supernova remnants, where asymmetrical debris clouds hint at violent rebound events. And in 2022, a team modeling FRB 121102 found its bursts could plausibly stem from a neutron star gradually consuming a fossil accretion disk, a scenario eerily reminiscent of fallback. The strongest criticism, though, comes from the bursts themselves. If fallback were the primary FRB source, we'd expect to see them concentrated in regions of active star death. Yet many FRBs trace back to galaxies with little ongoing supernova activity. Unless fallback can somehow operate in quiet cosmic neighborhoods, the model may only explain a subset of bursts. What keeps the fallback hypothesis alive isn't just its explanatory power, it's the tantalizing possibility that we've already witnessed it in action. In 2020, a magnetar in our own galaxy, SGR 1935 plus 2154, emitted an FRB-like burst alongside X-ray flares. While not a perfect match, the event showed how material interactions, perhaps similar to fallback, could trigger multi-wavelength outbursts. As telescopes probe deeper into supernova remnants and FRB host galaxies, the fallback model may yet prove itself as one thread in the larger tapestry of cosmic explosions. Until then, it stands as a compelling reminder: sometimes what goes up must come down, and when it does, the universe takes notice. FRB 121102 doesn't just repeat, it screams from one of the most chaotic stellar nurseries in the known universe. Nestled inside a dwarf galaxy 3 billion light-years away, this prolific repeater has made its home in a place where star formation explodes at rates that dwarf our Milky Way's quiet neighborhoods. This isn't just a galaxy, it's a cosmic pressure cooker birthing stars so furiously that supernova likely rock its skies every few decades, and that violence might be the secret ingredient fueling its relentless radio outbursts. Hubble Space Telescope observations reveal a host galaxy barely 1% the mass of the Milky Way, yet shining with the ferocity of a celestial blast furnace. The reason it's young, a toddler by cosmic standards, barely a few billion years old, and brimming with raw materials for stellar creation. Giant clouds of ionized hydrogen swirl through its core, lit from within by clusters of massive, short-lived stars destined to explode as supernova within millions of years. These aren't the placid, long-burning stars like our Sun. They're volatile giants that live fast, die young, and leave behind magnetars, the very objects suspected to power many repeating FRBs. What sets this environment apart isn't just the frenzy of star birth, but the aftermath. Every supernova explosion in this compact galaxy sends shockwaves tearing through nearby gas clouds, compressing them into new generations of stars while littering space with the magnetized corpses of dead ones. It's a self-perpetuating cycle. Each stellar death sows the seeds for more stars, more supernova, and ultimately, more potential FRB sources. The galaxy's small size amplifies the chaos. With less gravity to hold things together, supernova shocks can eject material entirely, creating turbulent bubbles of plasma that might focus or distort FRB beams as they escape. The smoking gun lies in the galaxy's metallicity, the abundance of elements heavier than hydrogen and helium. Measurements show it strikingly low, akin to conditions in the early universe when stars formed with purer, more volatile compositions. This matters because low metallicity stars tend to collapse into neutron stars with stronger magnetic fields, perfect for brewing magnetars capable of FRB production. It's a recipe found nowhere in our galactic neighborhood. Take a pinch of primordial chemistry, add a double dose of stellar violence, and let simmer in a gravitational cauldron barely large enough to hold it all together. Yet even here, mysteries linger. Among the hundreds of star clusters in this galaxy, why does only FRB 121102 stand out? Are other magnetars lurking unseen, their bursts pointed away from Earth? Or does this repeater occupy a special niche, perhaps near a supermassive black hole or within an especially dense nebula that turbocharges its eruptions? The galaxy's central region, where the burst originates, glows unusually bright in radio wavelengths, hinting at a magnetized maelstrom that could amplify or even trigger the FRBs we detect. The takeaway is profound. FRB 121102 might not just live in a turbulent galaxy, it might need one. Its host's extreme youth, frantic star formation, and chemical simplicity create the perfect storm for birthing and sustaining the universe's most enigmatic radio burst. Every time it repeats, it's not just sending a signal, it's offering a snapshot of the violent cosmic cradle that shaped it. And if other repeating FRBs trace back to similar environments, we might finally have a clue to why they echo while others fall silent. They're the rare survivors of astrophysical pandemonium, shouting to be heard over the din. Among the most exotic explanations for fast radio bursts lies a hypothesis so strange it sounds like pure science fiction. The idea that entire stars could be made not of atoms, but of hypothetical particles called axions, and that their catastrophic collapses might unleash the titanic radio bursts we observe. Axions, if they exist, are ghostly particles proposed to solve one of physics' greatest puzzles: why the strong nuclear force obeys a bizarre symmetry called charge parity conservation. Though never directly detected, axions are theorized to be incredibly light, possibly 1 trillion times less massive than electrons, and capable of clumping together in enormous numbers to form axion stars, cosmic objects as massive as our Sun, but with behaviors straight out of quantum fantasy. Here's where the FRB connection sparks. Under certain conditions, these axion stars could become unstable, collapsing in on themselves in a process called boson. Unlike a supernova's fiery explosion, a boson would be a silent, invisible crunch except for one critical detail. As the axion star implodes, its particles could convert into bursts of electromagnetic energy, including, the theory goes, precisely the kind of focused, millisecond radio flashes we know as FRBs. The math is startlingly elegant. the predicted energies align with observed FRB outputs, and the emission mechanism naturally produces the tight beams needed to explain why bursts are so bright yet so brief. Some models even suggest axion stars could account for both repeaters and one-offs, with partial collapses causing sporadic bursts while complete destruction generates singular events. But for all its theoretical appeal, the axion star hypothesis treads on shaky ground. First and foremost, axions remain purely hypothetical. Decades of searches, from underground labs to space telescopes, have turned up no definitive evidence they exist. Without proof of the particle itself, building stars out of them is like constructing a mansion on sand. Even if axions are real, their ability to form stable stars depends on poorly understood quantum interactions at scales far beyond our current computational abilities. Critics also highlight that while the model can replicate FRB energetics, it struggles to explain the intricate polarization patterns seen in many bursts, features more easily attributed to known magnetic environments around neutron stars. There's also the problem of falsifiability. Unlike magnetars or neutron star collisions, which leave behind observable remnants like X-ray afterglows or gravitational waves, axion star collapses would vanish without a trace. If an FRB appeared in a patch of empty space with no host galaxy, it could equally support the axion model or simply mean we failed to spot a faint dwarf galaxy. This ambiguity makes it nearly impossible to confirm or rule out the hypothesis with current technology, yet the idea persists, fueled by the sheer audacity of its implications. If even a fraction of FRBs stemmed from axion stars, it would mean the universe harbors an entire shadow population of invisible structures, stellar ghosts woven from particles we've yet to discover. It would also bridge two of physics' most pressing mysteries. The nature of dark matter axions are a leading candidate and the engines behind FRBs. That tantalizing possibility keeps researchers exploring the fringes, running simulations to test whether axion signatures could be hiding in existing FRB data. The axion star hypothesis may never graduate from speculation to settled science, but that's precisely its value. In pushing the boundaries of what's plausible, it forces us to question assumptions and entertain possibilities far beyond the familiar. Whether these phantom stars flicker in the darkness or not, their conceptual power lies in reminding us that the cosmos is stranger than we dare imagine, and that the next great discovery might come from chasing the most outlandish ideas of all. Not every cosmic radio flash is a genuine fast radio burst, and the hunt for FRBs has become as much about recognizing imposters as it is about discovering the real thing. The universe is full of radio noise, from the steady ticks of pulsars to the chatter of human-made satellites, and untangling these signals from true FRBs requires painstaking detective work. One of the most common cosmic mimics comes from a phenomenon called pulsar glitches, sudden speed-ups in the rotation of neutron stars. These ultra-dense stellar remnants typically spin with metronomic precision, but occasionally their crusts crack under immense strain, releasing pent-up energy that briefly revs up their rotation. The resulting electromagnetic hiccup can look strikingly like an FRB, especially if the pulsar's beam happens to sweep across Earth at just the right moment. But pulsar glitches have telltale giveaways. Unlike FRBs, which erupt from unknown distances, glitching pulsars often have well-documented positions and spin rates. Their signals also tend to repeat predictably, and their dispersion measures those fingerprints of intergalactic travel usually match the Milky Way's relatively thin plasma, not the thick soup of intergalactic space. The real challenge arises with extragalactic pulsars, whose signals might be mistaken for distant FRBs if their host galaxies aren't immediately visible. That's where multi-wavelength observations come in. A true FRB leaves no trace in optical or X-ray telescopes unless accompanied by a cataclysmic event, while pulsar glitches often come with afterglows or predictable counterparts. Human-made signals add another layer of complexity. Low Earth orbit satellites, particularly those using high-power radio transmitters, can produce bursts identical in duration and frequency to cosmic FRBs. In 2019, a burst initially flagged as extraterrestrial turned out to be interference from a passing satellite, an embarrassing but instructive lesson. Even ground-based sources trip up detectors. Observatories have logged FRB-like signals originating from everything from malfunctioning microwave ovens to military radar systems. The infamous Puritans, a series of millisecond radio pulses detected at the Parkes telescope, were eventually traced to staff members opening microwave doors mid-cycle, their electronics leaking radio waves that reflected off the telescope's dish. To weed out imposters, astronomers have built a verification toolbox. First, localization. True FRBs should appear in multiple telescopes simultaneously, ruling out local interference. Next, dispersion analysis. Astrophysical signals will show frequency-dependent delays proportional to the amount of plasma they've traversed, while terrestrial noise won't. Polarization acts as a third filter. Natural FRBs often exhibit complex polarization patterns twisted by magnetic fields, whereas artificial signals tend to be simpler. Finally, there's the ultimate test, repetition. While some FRBs do repeat, their patterns are chaotic compared to the clockwork regularity of pulsars or the predictable orbits of satellites. The stakes for verification are high. Misidentifying an FRB doesn't just risk embarrassing retractions, it could send researchers down theoretical rabbit holes, chasing ghosts instead of genuine breakthroughs. But every false alarm also sharpens the process, refining the criteria that separate cosmic marvels from mundane noise. In a universe where even a microwave oven can mimic a distant magnetar, the search for truth demands both skepticism and wonder, a balance that keeps the field honest while leaving room for the next great discovery. The future of fast radio burst research is about to explode into hyperdrive, thanks to a new generation of telescopes designed to crack these cosmic puzzles wide open. Leading the charge is the Square Kilometre Array SCAR, a revolutionary instrument spread across 2 continents, with thousands of antennas scanning the sky from South Africa to Australia. When fully operational in the late 2020s, SKA won't just detect FRBs, it will dissect them in real time, pinpointing their origins with accuracy down to a single galaxy, even a specific star cluster. Imagine catching not just a burst, but the magnetar flare or neutron star collision that birthed it, all while measuring the magnetic turbulence and plasma density along its path. This isn't just observation, it's cosmic forensics, but SKA is just one piece of the puzzle. The next decade will see a symphony of cutting-edge facilities joining the hunt. The Deep Synoptic Array in California, with its razor-sharp resolution, aims to localize hundreds of FRBs annually, mapping their host galaxies in unprecedented detail. Meanwhile, China's 500-meter aperture spherical telescope FAST is perfecting its FRB search algorithms, scanning deeper into space than ever before. Even space-based observatories are getting involved, with missions like ESA's Artemis planning to monitor FRBs across multiple wavelengths from radio to X-rays. Together, these instruments will transform FRB research from a scavenger hunt into a systematic census, revealing patterns and outliers we can't yet imagine. The biggest questions on the horizon: first, the repeater enigma. With enough data, we might finally understand why some FRBs echo for years while others vanish forever. SKA's sensitivity could catch ultra-faint repeaters lurking in quiet galaxies, testing whether all bursts have the potential to recur if given enough time. Second, the energy puzzle. Upcoming telescopes will measure FRB luminosities with such precision that we'll know whether magnetar flares can truly explain the most extreme bursts, or if something wilder, like quark star quakes or cosmic string snaps, must be invoked. Then there's the dark horse, polarization. future arrays will analyze the twist and alignment of FRB radio waves with atomic clock precision, potentially uncovering entirely new classes of magnetic environments. Imagine detecting a burst so twisted it could only come from a neutron star wrapped in dark matter filaments, or a black hole's ergosphere. Even more thrilling are the unexpected discoveries lurking in the noise, like FRBs that trace the cosmic web's hidden strands, or bursts so ancient they date back to the universe's first stars. The real game changer, real-time multi-messenger alerts. Imagine an FRB detection triggering instant follow-ups by neutrino detectors, gravitational wave observatories, and gamma-ray satellites all within seconds. This coordinated assault could finally nail down whether certain bursts coincide with neutron star mergers, supernova, or even, just maybe, phenomena we've yet to name. The next decade won't just solve FRB mysteries, it will redefine what we think is possible in the universe's most extreme environments. And somewhere in that flood of data, there might be a burst that doesn't fit any model, a signal so strange it forces us to rewrite the textbooks altogether. That's the thrill of the hunt. The next flash could be the one that changes everything. From the first enigmatic Lorimer burst buried in old telescope data to the rhythmic ticking of FRB 180916, from magnetars cracking under cosmic pressure to speculative action stars collapsing in unseen dimensions, fast radio bursts have rewritten the cosmic rulebook. These 30 mysteries aren't just scientific curiosities, they're radical reminders of how much we still don't understand. Every burst is a paradox, a signal so fleeting it lasts less than a blink, yet powerful enough to cross billions of light years. They challenge our definitions of energy, time, and even the fabric of space itself. Consider the contradictions. Some FRBs vanish without a trace, while others repeat with eerie precision. Some trace back to violent stellar nurseries, while others erupt from the quiet voids between galaxies. Some twist their radio waves into spirals, while others blast through the cosmos unfiltered. Each discovery peels back another layer, revealing not a single phenomenon but a spectrum of cosmic violence, a menagerie of astrophysical engines we're only beginning to catalog. The true gift of FRBs isn't just the answers they might hold, it's the questions they force us to ask. Why do magnetars in our galaxy produce feeble FRBs while distant ones unleash titanic blasts? Could some bursts be echoes from dimensions beyond our own? And what lurking anomalies might explain the orphans with no host galaxies? Every mystery defies complacency, proving the universe is stranger, wilder, and more inventive than our boldest theories. And here's the thrilling part: we're standing at the edge of a new era. With telescopes like the Square Kilometre Array coming online, the next decade could transform FRBs from cosmic riddles into keys to mapping the universe's missing matter, probing the hearts of neutron stars, or even uncovering physics beyond Einstein. The next burst could be the one that cracks the code, the signal that finally makes sense of the chaos. So stay curious, keep looking up, because somewhere out there, in the darkness between the stars, another flash is coming. A pulse of energy fired across the ages, carrying secrets we've only begun to imagine. And when it arrives, it might not just change what we know about FRBs, it might change what we know about everything.